This is AP Calculus BC, and in this video, I'm going to talk about section 4.5. In your book, they call this applied max and min problems. In most calculus textbooks and calculus reference materials, they refer to these as optimization problems. So when we go through this is going to be a lot of problem solving, and it's similar to what we did with related rates. I can't possibly show you every type of optimization question you're ever going to see. So what we're going to focus on here is really just an overall strategy as opposed to more of an algorithmic formula or process that you follow every single time. So that's not going to be the case for these problems, because every problem can be different. Sometimes we're going to be dealing with geometry. Sometimes we're going to be dealing with trig. Sometimes there's going to be a lot of algebra involved. A lot of times the questions are combinations of all of those things. And then there will be a little bit of calculus within the problem. So what I want to do is show you a couple of examples and then have you try a couple of these examples. So the first one that I have here is a really common type of optimization question. It says a manufacturer wants to design an open-top box having a square base and a surface area of 108 square inches. What dimensions will produce a box with maximum volume? Okay, so they already gave us a diagram here. That would typically be my first step, just like with related rates. So we know we're talking about volume, and you can see the area of the base would be x squared and the height is h. Okay, so simple volume. Now, they also gave us some information about surface area. Now, I know I'm trying to maximize the volume, so that's really what I want to be working with. But the surface area is serving as what we call a constraint. So we have this constraint that the surface area has to be 108. So I know that the area of the base is x squared, and the area of the four sides, they're all x times h. Now, when they say surface area, they're really, in these problems, typically referring to the amount of material that we're going to use, or you can think of it as the exterior surface area. We're not really talking about, the amount of area that, if you want to think of painting the faces, that's not really what we're thinking about from a surface area perspective. We're really just talking about the area of the pieces that create this box. So we know that total has to be 108. Now, notice right now I've got a volume function which I want to maximize. Using what we've done the last couple of classes, if I want to find the maximum, I know I want to take a derivative and I want to find critical points. The problem is my volume is in terms of two variables right now. So what I'm going to do is I'm going to use my constraint to try to come up with an expression for the height that will allow me to then do some substitution. So I'm going to take this information that I have about the surface area and I'm going to solve for h. H would be 108 minus x squared. Let me rewrite that so it's a little neater. Minus x squared divided by 4x. And if I simplify that down, that's the same as 27 over x minus x over 4. Okay, so now I've got an expression for h. So I'm going to rewrite my volume function now so it's in terms of a single variable. That means the volume is the same as x squared times 27 over x minus x over 4. And if I multiply that out, I'll end up with 27x minus x cubed over 4. Okay, so now I've got a really simple volume function that I can work off of. Okay, so now it really turns into a little bit of calculus, because now how do I find the maximum of this function? Well, I take the derivative, which would be 27 minus 3x squared over 4. And I'm going to set that equal to 0. I'm trying to find critical points. So this is the same as 3x squared is equal to 108. And when I solve that out, what I would end up with is x is equal to plus or minus 6. Now, when you first look at that, it appears that we have two critical points. But since we're in a problem-solving scenario, keep in mind what x represents. X is the length of a side. So there's no way x can be negative. So that negative 6 is not something that I really need to deal with. I'm going to do a sign chart just to verify that I'm getting a maximum like I'm expecting. But here's my sign chart, and I'm only going to test around 6. So really I'm thinking between 0 and 6, and if you even wanted to put an endpoint on here, you could. Between 0 and 6, and then anything higher than that. But you can see when I have a number that is between 0 and 6, like let's say I plug 1 in. If I plug that into my derivative, I'm going to get a positive. As soon as I get higher than 6, my derivative becomes a negative. So I can see from that sign chart that I have a maximum when x is equal to 6. So the question said, what dimensions will produce a box with maximum volume? Well, it would be x has to be 6, and that was in inches. And using the substitution that I had earlier, I know that h is going to have to be 3. So those are the dimensions that would produce the box with a maximum volume with the given constraint that I had. Okay, so it's not super difficult to solve these out. This is a relatively straightforward question. The hardest part of this is always figuring out what your function is and getting your function in terms of a single variable. So we do have an overall strategy that we can follow. And this is in some ways similar to what we did with related rates, where I'm not going to try to teach you every type of optimization problem you'll ever see, because I can't, but I can give you a strategy to follow. So what I would like for you to do as a habit is draw a picture. That's going to serve as helping you visualize what's happening. It's also going to define your variables. We're going to write the equation of what we're trying to maximize or minimize. If needed, we'll convert to a single variable. If you want to specify a domain at that point, if it's obvious what your domain is at that point, you can specify your domain. Step 4, we're typically not going to do, because these are typically non-calculator questions. If you have a calculator, you could definitely do step 4, but typically we won't. So then we're going to find critical points, which is what step 5 is, and then we're going to test critical points and endpoints if we have any endpoints. Okay, and then the last step, notice that it says be sure to answer the question, because a lot of times you'll go through and you'll find X, and maybe that's not what they're asking you for. So make sure you actually ask the question that was, or answer the question that was originally asked, and then make sure that your answer makes sense. Because we're working in a problem-solving scenario, it's easy to look at the size of your values and see if they make sense. For instance, on this last one, when I got x is 6 and the height is 3, it's easy for me to check, first of all, that I get the correct volume, but it's also easy to check that those numbers seem reasonable based on the volume that I'm given there. Okay, so let me show you another question. This is really the most basic type of optimization question. This doesn't even have really a lot of problem solving involved with it. You can jump straight into the equations here. It says find two numbers whose sum is 16 and whose product is as large as possible. So I don't have to really think about drawing a diagram or anything like that, because they pretty well told me exactly what I'm doing here. So I want two numbers whose sum is 16 and whose product is as large as possible. I'm going to call my numbers x and y. And they told us we have this constraint that x plus y has to equal 16. Now remember, I'm trying to maximize that product function. So right now it's in terms of x and y. If I were to solve this constraint equation for y, y would be equal to 16 minus x. That means my product function is the same as x times 16 minus x, and that's the same as 16x minus x squared. And now I can take the derivative, which would be 16 minus 2x. I can set that equal to 0, and I get x is equal to 8. I'm pretty certain that that's going to be my maximum, but you could always go through and do a sign chart and just make sure, do I have an actual maximum here? And you can see if I have a number less than 8, like let's say 7, that would give me a positive derivative value. And if I have a number larger than 8, I'm going to get a negative derivative value. So I can see there is actually a maximum at 8. So they asked me for the two numbers. So the two numbers, x would be 8 and y would also be 8. Okay, so pretty simple to do when you have those types of questions. That's really sort of the easiest type of optimization question you're going to get. And at the beginning of your homework, you'll see a couple like this, just to get you used to really what the process is that we're trying to achieve when we go through these problems. But as you work through the assignment, you'll start to see more and more problem-solving scenarios starting to pop up. So what I want you to do is I want you to try this next one. It says a rectangle has its base on the x-axis, its upper two vertices are on the parabola y equals 12 minus x squared. What's the largest area the rectangle can have, and what are its dimensions? So remember, start with a diagram, but I want you to pause the video, solve out this problem, and then when you come back, I'll show you the solution. Okay, so here's what you should have ended up with on that one. Notice in my diagram, I've got the parabola opening down. You can see I went x units to the right and x units to the left, and you can see I've got just an arbitrary point on my parabola of x 12 minus x squared. So really, I can jump straight into an area formula this time because of the way I did my diagram. And you can see my area, the base is 2x, the height is 12 minus x squared. So I've got my area formula. Just in terms of x, took the derivative, set it equal to 0. I know x can't be negative. So the only point I'm really interested in here is this one. I don't really care about the rest of that sign chart. So when I'm looking at 2, I can see 2 as a maximum. Notice I went out to root 12. The reason why I went out to root 12 is because I know that my vertices have to be above the x-axis. So the x-intercept is at square root of 12, so I know I don't want to go past the square root of 12. So definitely there's a maximum at 2. Now, the mistake a lot of people would make is they'd say, okay, well, x is equal to 2 is my answer. But remember, the question says, what is the largest area the rectangle can have, and what are its dimensions? X isn't even one of the dimensions. So you wouldn't have any of the answer yet if you put x is equal to 2. The dimensions, remember, are 2x by 12 minus x squared. So my area would be 32, and my dimensions are 4 by 8. Okay, not super difficult to do, but starting to get into things that are a little more challenging. Once you have a good diagram, it becomes pretty obvious what you need to do to solve the problem. Okay, so there's one more I want you to try here. This one, it says, which points on the graph of 4 minus x squared are closest to the point 0, 2? And I put a hint there for you. So again, I want you to pause the video, and I want you to try this one. Okay, so here is the solution that you should have gotten for that one. Now again, notice on my diagram, remember when I went through in class when we had the problem from your quiz that had the tangent line, and I told you you can choose an arbitrary point? That's essentially what I did here, is I have an arbitrary point on the parabola of x 4 minus x squared. So now I just used the distance formula between the point 0, 2 and my arbitrary point, and I came up with a distance function. Okay, so that's what I have right here. Now, like it says in the hint, if I can, in this case, I'm trying to minimize the distance. If I can minimize what the radicand is, then it's going to minimize the overall function. So what I did was I just defined a new function r to be my radicand function, and now this is all I have to work with. I don't have to mess with all that square root stuff. So I took the derivative, I set it equal to 0, and I got 3 critical points. I don't really have constraints this time in terms of x can't be positive or negative, so I want to make sure I account for all those values. I did my sign chart, and I can see that I'm getting a minimum here where I'm at negative root 3 over 2, and also when I'm at positive root 3 over 2. And it turns out you get the exact same y coordinate for each of those, as you would expect, because you're dealing with a parabola, and you would expect that you would have 2 solutions because you're going to have solutions that are mirror images on either side of that parabola. So in the end, I got plus or minus root 3 over 2, 5/2. And again, since I have a graph, it's easy to check to see, does this look like it makes sense? Does that seem reasonable based on the shape of that graph? And I would say, yes, it seems reasonable. So make sure you always check that at the end. Make sure your answer seems like it makes sense. All right, and then the last problem I want to go through here with you is just a little bit different type of question. Now, this diagram has some extra information on it because this came from a book that had a question with multiple parts to it. So there's some extra information we'll have to just sort of ignore here, and I'll explain that to you. But this is what we call a minimal path problem. The reality is the way this one's worded is more of a minimal time problem, but it's typically referred to as a minimal path problem. So they're talking about someone who's in a boat, and they're trying to get to a point down the coast and 1 mile inland. Now, it's a little bit confusing here with the way that this thing is, because this was a diagram that was in color, and now I've got it in black and white, so it's kind of hard to see, but your shoreline is right here. That's your shoreline. Okay, so what we want to do is, knowing how fast he can row and how fast he can walk, we want to figure out what's the fastest way to get to the point from where he is to the point Q. Okay, so keep in mind, if I'm thinking about how long it's going to take, there's going to be an amount of time that he spends rowing, and there's going to be an amount of time that he spends walking. Okay, so those are the two things that we need to account for in our function. And since he rows and walks at different rates, we're going to have to account for that when we figure this out. Now, the nice thing about this is the diagram's already been done here. Typically on these problems, the diagram's not already done. So let me just explain what's in here. So it says that he's trying to go to the point Q, 3 miles down the coast and 1 mile inland. And notice that the distance he is from the shore is 2. And then across to this point, we're saying is X units. So that means the distance that he's going to row is the hypotenuse of that right triangle. It'd be the square root of X squared plus 4. And then the distance that he is going to walk is going to be this part of it, that hypotenuse, and that would be the square root of 3 minus X squared plus 1 squared. Okay, so those are the distances that I want to deal with. Now, notice it says up above here, distance is rate times time. That means time is distance divided by rate. So for my function, if I want the time rowing, I need the distance rowing, which we said is going to be X squared plus 4. And we want to divide that by the rate he can row, which was 2 miles an hour. Same thing with the amount of walking here. We know the distance is going to be 3 minus X squared plus 1. And that's all going to be divided by the rate he can walk, which was 4. So there's my time function. And now I just go through the same process. I find in this case, the minimum. So I can take the derivative, set it equal to 0, go through that whole process. I believe the answer on this one is time is equal to 1. I'm not going to go through all the steps, because once you get to the point where you have the functions written out, basically every problem becomes the same. It just turns into a max-min problem. But getting to the point where you have the function, just like it was with the related rates problems, getting to that point where you have the function is the hard part. Once you have the function, process becomes the same every time. Take the derivative, set it equal to 0, account for domain, and then test around those points. Okay, so I did include a worksheet here, just like in the related rates problem solving section. This is just extra practice, primarily so you can see the level of question that I expect you to know how to do. Start with what's in Wiley Plus, and then you can use this as a supplement if you feel like you need more practice, or you want to feel like you really have practiced a lot of the types of questions that I might ask you. You can work on these. I do have the solutions here to the worksheet in Schoology, and I also put them on the class calendar, so you can access them in both places, so you've got the answers when you work through those.